very excited. I've been wanting to talk about diamonds for a long time, even made my nails look like them. I'm so pumped that we
Woohoo!
have Lyn joining us today. Yeah, so it's going to be a lot of fun. And I'm very excited that we have Lyn Takenaka with us today. So Lyn is a consulting geologist with SRK Consulting, and with over 9 years experience in geosciences, and having finished her double PhD in Australia and Brazil, it went into the origin and composition of the lithospheric mantle in very complex geological settings. She combined a large range of techniques such as geochronology, geophysics, geochemistry, statistics, programming, and much more to solve a historic diamond exploration enigma, while also proposing new geological concepts and methods. So with all of her insights, it is going to be amazing to have this masterclass with her today for all that we've ever wanted to know about diamonds. So it is going to be an awesome session. I hope you all enjoy it. Please use the chat and we'll open up the floor at the end. But before we get stuck into your presentation, Lyn, firstly, thank you so much for joining us today. But I was very curious what got you into geology in the first place.
Well, long time ago, when you're searching for career, I always knew that I liked it a lot, chemistry, physics, but I also really loved the geography, the physical geography, and understanding the Earth. I always watched tons of documentaries, even as a kid. And I went to a class one day, and I saw this person presented what was a geologist, what was the role of a geologist, which was knowing all about the rocks and how the earth was formed, and even out of the earth as well. So that got me very interested. And since then, I noticed that I could use all my chemistry, physics, mathematics, everything if I wanted to. And then I just got in love. So that's pretty much it.
I love that. That's an awesome story. You're born with it. You've loved it all the time.
Exactly.
That is amazing. And so you've been busy doing a double PhD from Australia and Brazil. Congratulations on that. Is that all, yeah, all finalized now?
Yes, yes. Yeah, thank you very much. Yes, last year I finished all the celebrations, and I still have some publications to go on, but the degree itself it's over. So there's still some things to come up
Yeah.
the
That,
next years. Yeah.
how exciting. Yeah, that's very, very impressive. So I cannot wait to hear from you today. Yeah, and get all of your knowledge about everything diamond. So thank you so, so much. If you want to share your screen and we'll get stuck into it.
So good afternoon, everyone. It's a big honor to be here today. So thank you, Geohug, for this lovely invitation. Before I start, let's have a look at this beautiful set with 9 diamond cuts that I have on the screen. And as most of you might know, they derive from the largest gem quality diamond ever found, the Cullinan. And the original crystal was discovered about 120 years ago in South Africa's Premier 2 kimberlite and weighted around 3,106 carats, which is equivalent to 621 grams. So Cullinan became the most iconic symbol of luxury and power of our time, thanks to this woman, as you might know. And now let's put aside a little bit of this royalty matters to talk about geology. I have here an image that shows the weird type of rocks that we expect to carry natural diamonds. And today I want to show you not only where we can find them, but also their fascinating relationship with the deep layers of the earth. We will talk a little bit about the geological process behind and the real reasons why diamonds are so special. So let's break through. The first question is, where are they? So I'll talk about the past and present hotspots in the world where we can find them. And we believe that the first diamonds were recovered thousands of years ago in India. and that was probably the only supplier in the world until 1725, when significant alluvial deposits were found in Brazil. For over 150 years, Brazil was the world leader, but the scenario changed drastically in 1871 when in South Africa they discovered these diamondiferous host rocks named after kimberlites. After that, many other kimberlites and deposits were discovered all around the world, and that shaped the scenario we have today. So many of these historical diamond producing diamonds, they still have hard rock active mines. And some we have here a representation of the main hard rock diamond mines around the world. Some are active, some are not active anymore, like Argyle in Australia just ended its operations in the past 1 or 2 years. And as you can see, Russia is the world leader in the rank of diamond production, followed by Botswana and Canada. So what is the correlation that we have between those locations and geological settings? Let's observe this set of diamonds found in alluvial deposits of the southeast Brazil. I really like this picture because it's summarizing the reason why I did my PhD in the first place. So it was to define the enigma around those rocks, those minerals, and the variation in color, shape, size, and materials trapped within the crystals show us how diversity and inclusion of the different populations reflect their complex and different origins. We can also say that diamonds are not shallow and form in many different ways. So we'll be back to this later on, but we're going to look at those, we're going to look at diamonds as forming in a deep earth, and these can either be in the lithospheric mantle, about 150 to 100 kilometers, relate to thick and cool roots of the continents, not necessarily old. And there are also some different kind of diamonds that form even deeper, which the super deep diamonds found in the transition zone. So these materials are all carried to the surface by very special volcanic eruptions called kimberlites, but there are also other volatile rich rocks related. And they bring all these xenoliths and xenocrysts, which are little pieces of the mantle, and the diamond itself is not formed in the kimberlite, it's just carried away. So kimberlites are very special types of volcanoes, not like the volcanoes we see, for example, in Indonesia or in the Ring of Fire. And they have this carrot-shaped profile, as you can see to the right. And they are hybrid rocks of explosive nature, hence they drag everything they can from depth to surface in a relatively short period of time. I would like to acknowledge that the mechanisms of formation and intrusion of kimberlites, they were very enigmatic. And just recently, Professor Thomas Gennon published this amazing work about what would be causing these eruptions. So I'm not going to enter in details. If you like, the references up there. But in a nutshell, his model suggests that the rifting processes generate convective instabilities in the asthenosphere, and that slowly migrate for many kilometers inboard of rifted zones, generate this small volume of low degree volatile rich melts. And as you can see, this, for example, occurs along structural corridors in Brazil and Africa, This is part of my PhD thesis, so I've studied some of those rocks up there. This graphic shows that we also have not only the host rocks carrying the diamonds, but also the secondary process of erosion and transportation, removing the diamonds from these primary sources and accumulating them in riverbeds and alluvial terraces or the secondary sources. And the degrees of how you can check the diamonds and see how were they altered by these transportation processes to try to define if the sources are proximal or distal. And the difficulty with these deposits is that they have very random patterns of concentration. So as you can see here on the right, I have graphics showing the large distribution of diamond size and a large number of crystals removed from Brazil in the region I did my PhD. But it's really a mystery on how to recover them and where they came from. So this is just a map summarizing how we have these distinct diamond types and distinct sources and across all over the world. And they are not necessarily correlated to what people believed in the past, just the cratonic blocks, the old cratonic blocks. So what is the timing of formation for both the diamonds and the host rocks? Okay, so regarding to the timing of the host rocks and diamonds, I would like to introduce you guys to this paper, which I just published in Gondwana Research, showing that we can use a very wide range of geochronometers and isotopic systems to define the age of these rocks. Same thing for the diamonds, but a little bit different. I will tell you later. And I suggest in this paper a multi-mineral geochronology together with chemical and microstructural analysis, just to provide tools for a robust interpretation. And the reason why is because some of the systems are disturbed or represent all the events before the magma crystallization. So here we have pretty much the Earth clock, because it was recognized by a few authors that the time of eruption of kimberlites and related rocks have a pattern which pretty much correlates to the supercontinent cycles and also the lithosphere thickness. And for diamonds, time is pretty much relative. I'm not going to enter into much details, but I brought these graphics from Smith and Shirey 2020, showing that the diamonds are formed pretty much in all type of age ranges, starting from very old diamonds like Ekati Diavik 3.5, 3.3 giga years to nearly today, let's say like that, 65 million years. And then we can obtain the diamond's ages not directly, because their composition, the elements, there are impurity in their composition, don't allow us to do that. So we use these entrapped minerals in the diamond systems, which are silicates, sulfides, and super deep mantle minerals in a different range of isotopic systems as well. So the diamonds can tell us a little bit about fluid sources that can be useful for diamond exploration, and we might notice that multiple generations of diamonds can form within the same deposit. So are diamonds forever? I know that there is a big connotation from the years with advertisement campaigns about diamonds being forever. And we can pretty much tell you that they are not. So apparently diamonds, they have this wide variability, and they are affected by fluids and other things along their history. And for example, there is something called resorption that is an alteration. And if these fluids are strong enough, they can actively um, vanish the diamonds. So you would have, for example, kimberlite intrusions bearing, and we need to make sure that these intrusions bring the diamonds which are preserved, and they were also fast enough to overcome the dissolution process. So we have these papers here if you want to check more about that. And how did that all happen, all of these processes and everything? And I like to call it the Earth's jewelry box, which is pretty much the subcontinental lithospheric mantle. And this was the focus on what I have studied during my PhD, because the subcontinental lithospheric mantle is this non-convective part of the uppermost mantle that is together with the crust. So it is chemically, thermally, and mechanically distinct from the underlying asthenosphere, and it participates of all these essential geological processes on the Earth. And it also contain potential for not only diamonds, but all forming elements, forming different mineral resources. And we can also use the mantle to study different earth cycles because it's everything connected. So I am also not going to bore you guys with all the details about that, but this subcontinental lithospheric mantle evolved through time. So the first stable lithospheric mantle was formed in the Paleoarchean by large melting events, forming these buoyant, highly depleted reses of cumulates. And we know for a fact that at least 70% of the subcontinental lithospheric mantle was formed in this very short period of time. And we had this change in compositions and processes following up the changes in tectonic settings from old style tectonics to what we call modern style plate tectonics. So the SSLM is pretty much dominated by peridotitic ultramafic rocks. It may contain aluminous phases such as garnet and spinel. And garnets are the xenocrasts that can tell us something about the source rock types, depletion of fertility, metasomatic processes. Normally, this metasomatism is divided in different types of melts, but other processes in the like infiltration of asthenospheric melts and etc. are recognized. Also, in terms of composition, the mantle follows secular variation, and it's geochemically very complex. And as you can see here, there's a difference in composition from the oldest subcontinental lithospheric mantle to the most recent ones. Also, garnets from regions with different ages and tectonic settings can reflect distinct correlations between composition and tectonic thermal age, which represents the last major perturbation in the overlying crust. So for that, I have used a lot of this during my research. It was adapted, this Genesis 1994 classification for the main distinct suites of subcontinental lithospheric mantle, which are archon, proton, and tecton. And if you observe the conductive polygeotherms, we can see that the thermostat and the thickness of the lithosphere is also strongly correlated with the tectonothermal ages. And also, the density is expected to be lower or more buoyant in archon localities. Another thing that's correlated to the mantle, and it's quite of a complex topic, is oxygen fugacity, which refers to the oxidation state of the subcontinental lithospheric mantle. And this can be measured by redox proxies, this buffers over here. And it represents pretty much all the differences in physical, chemical activity, such as melting, composition, speciation, and others. And we know that under modern conditions, the distribution of the oxygen fugacity is very heterogeneous, but the oxidation state possibly decrease with depth. So I just would like to show you guys that whoever is coming to the next Kimberlite conference, I will be over there presenting what we developed during my PhD as a new possible oxybarometer for the subcontinental lithospheric mantle based on garnets and ochres. So I guess that will be very interesting. And so how is the geological crafting forming the actual diamonds? So diamonds are one of a kind. So we have this cartoon that is very famous, just showing that the family is telling the dad that he's been under a lot of pressure lately. And that is true to say that diamonds are pretty much carbon, and so it is graphite. But the difference is that the atoms bond in the specific way, and this makes a difference in the physical properties. For example, diamonds are the highest hardness, and graphite, in the other hand, is not. And also impurities, defects, and inclusions in these diamond crystals, they cause these variations in colors that you see, for example, pink, blue diamonds, and so on. But they pretty much form under higher pressure and higher temperature conditions. And as a consequence of that, we have what we call a diamond window, which is the favorable depth of formation of these diamonds. We also know that for a fact, most of the diamonds we recover nowadays, they are related to lithospheric sources, which firstly are peridotitic, but also can be hasmogitic or eclogitic. And for example, the peridotitic sources are responsible for this very common type of diamonds, which are the type 1 diamonds. And they are higher in nitrogen impurities. So as you can see in the cartoon on the right side, showing a little bit how this process could work, we have a progressive metasomatism playing an essential role in the diamond genesis and destruction. And we pretty much just need the right amount of fluids percolating in the system to have also a little bit of luck that the kimberlites at the right time and location carry them up. given that diamond dissolution is common, we need to make it a friendly environment for the diamonds to grow. As for the type 2 diamonds, which are the other ones down here, they have significant lower nitrogen and are from much deeper sources. But I would like to introduce you also to this very special kind of diamonds recently, not so recently, but proposed by Evan Smith. And it's a category that he calls the acronym CLIPPY, which refers to colonial-like large inclusion pool, pure, irregular, and resorbed diamonds. And they can include a few of the type 2A diamonds. They are formed under highly reducing metal-saturated conditions above 360 kilometers, and they are evidence of that are the presence of these metallic melts, and they are very relevant because they bring these very large gemstones which everybody's looking for. So this is just a cartoon from the beer showing representing how this all the systems are connected, and if kimberlites erupt in the wrong location, they will become different types of, they will not bring the right amount of source of diamonds. And why do we care? So I just would like to show you guys a brief understanding that diamonds are much more than just engagement rings or jewelry, and they are also very important for lithosphere studies and for the scientists in general. So just bringing again all the top 10 diamond producing countries in the world, you see that there is a high value attached to the production of these diamonds. And also here there's some plots showing the average spend of money in engagement rings, which can be pretty high. And also something that is very widespread, which are the 4 C's of diamonds, representing carat, clarity, color, and cut. So that's what they use to evaluate and give value and put prices in the market pretty much. So I got this little joke to say that the diamond is the what we call the Earth's coat. So why did the diamond become the Earth's coat? Because it wanted to help all this to shine. So obviously that for us scientists, understanding the Earth is something very desirable, and the diamonds allow us to see through layers and materials that we cannot directly access. So we have, for example, discovered the diamonds associated with water in the subcontinent, in the mantle, in great depths. So this super deep diamonds, for example, they can reach to the transition zone and collect the little small samples from these layers and bring it up. So I'm not going to describe in details what these studies are, but there's tons of studies relating diamonds and the host rocks as well, the kimberlites, to all the subcontinental cycles and all the important studies that we use not only for science but also for the industry. And the reason why diamonds are so special is because they are hard, they shine, they are rare, and they have been symbol for over thousands of years. And whatever it is that people attach to that, if it's power, luxury, love, it also helps us to understand the geological processes and find all the deposit types. So we also can use these studies to understand different deposit types which are not diamond related. And as I said, access all these deep layers of the earth. But just in a quick summary, I would like to show you how do we do exploration, and great majority of the companies base their search in what we call heavy mineral indicators. These disaggregated minerals from the host mantle rocks, and can be all this wide range garnets, chromites, and others. And the difference is that they are very abundant, so we can cover a bigger area and find for diamonds on a more wide way than just looking for the diamond itself. And these are just diagrams that people use to classify, for example, the garnets and the chryse sources. And they just distribute the different rock types associated with different compositions of the garnets, as I said before. And in the case of low chromium garnets, different types of garnets, it's not that well constrained, but you also have some specific diagrams for that. And also after that classifications, you can usually put the xenochrist on a pressure and temperature depth context. And for example, in the case of single grain geotherms, we can use single grain thermometers and barometers, so that we can build these empirical geotherms, and they give us clue on the geothermal gradients at the time of the eruption. And all the garnet mineral chemistry data can also be used to construct these different zones of different rock types, and using statistic methods together with other things like geophysics, etc. You can do something that we call lithosphere mapping, and this can be in multiple dimensions, in 1 dimension, 2 dimensions, and even the evolution of that through time. So I just summarizing here that convention exploration usually uses geophysics and the so-called chemical tomography, which is the use of all this chemistry of these heavy minerals. There is also a lot of studies on the petrography of these kimberlites and related rocks as well. Here there's a very nice glossary that is very well known within the community, and our SRK people from Canada, there's some of them over there as well. And as you can see, there are many different ways, but the main point is that, as I show you guys, the diamonds are very complex, and they can form in different ways, in different depths. And the conventional exploration possibly doesn't cover all of the diamond types. So just leaving you with this thought on where should we look next, and the distribution of the diamonds. For example, the super deep diamonds go in different locations, and maybe that's where we need to vary methods and discover new ways to find them, because we're not looking at the subcontinental lithospheric mantle anymore, and the conventional methods are possibly not going to work that well for the exploration of these diamonds. But at the same time, they also bring that big crystals, which are very desirable by the industry. So that's all for today. I hope you learned about some basics concepts, and thank you very much. Is my contact if you need anything, have any question.
That's excellent. Thank you so, so much. I really appreciate you talking to us.